Okay, so today we're going to begin the part of the course which is usually called point set topology. So point set topology is concerned with properties of general properties of topological spaces. The main ones that we're going to consider are compactness and connectedness for spaces. But before we get to that, we need some more terminology. So let's start with X, a topological space. And let's fix A, some subset. And X, any point in X. So there's something which we'll call the subset trichotomy. Which describes the way that X and A interact topologically. So either well, here's the possibility. So either there exists an open set U so that X is in U and U is contained in A. That's the first possibility. Or there might be an open set U so that X is in U, which is contained in the complement of A. So this is X minus A. Or it might be the case that every open U containing X intersects both A and A complement. So in this first case, we say X is an interior point of A. And here we say X is an exterior point. And so in this third case, well, we're going to split this case into two further cases. So if every open set containing X intersects both A and A complement, one of two things happens. So then either there exists an open set U so that U intersect A is just the singleton X. Or it might be the case that every open set U contains containing X contains a point of A minus X. So in this first case, we say X is an isolated point. And in this second case, let me put this over here, we say X is a limit point of A. Okay, so this is some terminology which will be useful. Let's see an example. Let's see a couple examples. So first, let's take X to be R with the standard topology. And let's consider A the following set. Okay, so we have R and here's A. Like this. Let me use some colors. Okay, so this is A. Right, so let's figure out all of the different, which points are, so this is a trichotomy, or I guess it's a quadcotomy, whatever. There's 4 cases. Every point is either an interior point, exterior point, isolated point, or limit point. Let's see which points are which. So first of all, the interior points. Well, okay, so these are points for which there exists an open set around that point, which is contained in A. And so, well, you can see that any point in the interior of, well, let me not, yeah, so this, any point in this interval 0 to 1 is an interior point. And these are the only ones. The exterior points, well, now we have, well, a point, any point out here is an exterior point. There's an open set around this point, which is in the complement of A. And similarly, points here and points further out over here. So the exterior points are, so minus infinity up to 0, not including 0, together with the interval from 1 to 2 and the interval from 2 to infinity. Okay, so then isolated points and limit points. So there is an isolated point here. Namely 2. And that's the only isolated point. So there exists a neighborhood of 2 here so that it intersects A only in the point itself. So that's being isolated. And the rest of the points are limit points. So which points haven't we covered so far? Well, that's 0 and 1. And so by definition, these have the property that any open set, so any open set around 1, no matter how small you choose it, is going to contain points of A and of A complement. So a couple of observations, or maybe just one observation. So note, well, limit points can be in either A or A complement. So both are possible. So interior points are always in A, exterior points are always in A complement. Isolated points are always in A by definition. Here. And then, but limit points can be in one or the other. Okay. Let me do one more quick example. Let's take A to be the ball of radius 1 around the origin in Rn. So in this case, the interior points is all of A. Every point is an interior point. So let me draw a picture in the two-dimensional case. I should draw it dotted to indicate the boundary is not included in A. So here's A here. Right, so any point in A is an interior point. You can find a small ball around this point, which is fully contained in A. Any point, so the exterior points are, well, points of norm greater than 1. Points distance greater than 1 from the origin. So if you're distance greater than 1, well, yeah, again, you can find a small ball contained in A complement. And the rest of the points are limit points. And those are the points at distance 1 from the origin. And again, it's not hard to see that for such a point, any ball around that point or open set intersects both A and A complement. Okay, so in this example, there's no isolated points. Okay, so next I want to prove a little lemma which gives some further intuition for what it means to be a limit point in the special case when X is a metric space. So let's assume X is a metric space. For example, you could just think X is Rn with the standard metric, but this holds quite generally. So X is a limit point of A. Okay, so and we fix A and X. If and only if there exists a sequence which I'll write like this. So this is a sequence of points in A that converges to X. And actually these points should be in A and not in X. So let me, so A1, A2, and so on in A minus X. That converges to X. So converges means here that given epsilon greater than 0, there exists some large number n, so that for n sufficiently large, the distance from an to x is less than epsilon. So the picture is we have x and we have some sequence of points in the space, or here we're assuming they're in A, and this sequence converges to X if, well, given any epsilon, for all sufficiently, eventually all the points lie in this epsilon ball. So here you have A1, A2, etc. And this definition of convergence says that eventually, and that's what this n is indicating, all the points lie inside this epsilon ball. Okay, so there's this sequence interpretation of being a limit point of A. Okay, let me prove this. Let me make space here. Yeah, so let me explain the proof of this. So in the forward direction, if x is a limit point, so let's assume x is a limit point of A. So we want a sequence of points that converges to x. And the way to do that, to get such a thing is, well, let's consider, well, so x being a limit point means any open set around x contains a point of A other than x. So let's consider these particular open sets. So by assumption, let me say it this way. So x being a limit point, then this implies that this contains some point, let's call it an in A and not in X. So then, well, this sequence converges to X. Yeah, I mean, the distance from an to x is less than 1 over n. So in particular, given any epsilon, if you just take n so that 1 over n is less than epsilon, then you satisfy this. Okay, so that's not so bad. On the other hand, so the converse, so let's suppose that, so assume there exists this sequence an converging to x. So an is contained in a minus x converging to x. Okay, so now we want to show x as a limit point. So let's fix u open containing x. We want to show u contains a point of A other than x. Yes, so the way we can do this is, well, first there exists some epsilon, since u is open and it contains x, there exists epsilon so that the ball of radius epsilon around x is contained in u. And then by convergence, there exists some n so that if n is greater than n, that implies an is in the ball of radius epsilon around x, which is contained in u. And so here we've found a point of A other than x, which is in u, and that completes the proof. Okay. So let me give you an example for how this lemma is useful for showing certain points or limit points. So example. Let's take x to be r and a to be the rational numbers. So then every x in R is a limit point of A. And there's different ways you could argue this, but it's convenient to just use sequences. So we can see this by writing x as in a decimal form. And well, okay, so now let's find a sequence of rational numbers that converges to x. Well, let's take A1 to be this and A2. So we just truncate the first n decimals. Maybe I shouldn't call this n, but okay. And so on. So this is a sequence converging to x. It's sequence of rational numbers converging to x. Okay. Okay, I want to make one observation here about, one more observation about this trichotomy. So in terms, we can phrase what it means to be open in terms of this trichotomy. So this is an observation. A subset A in X is open if and only if every point of A is an interior point. So let's think about this. So the forward direction, this is immediate, because if you're given X in A, we can take U is A, that's an open set contained in A, which contains X. So every point is an interior point. On the other hand, if every point, so if every point is an interior point, then for X in A, there exists some UX open where X is in UX is in A. And then A is the union of all of these. And these are open, and unions of open sets are open. So A is union of open sets, hence open. Okay. So next I want to introduce one more piece of terminology related to this subset trichotomy. So definition. So we say that a subset of X is closed if it contains all of its limit points. So for example, this set that we considered before in R is not closed because it doesn't contain its limit set or limit point 1. On the other hand, well, if we just add this point in, now it's closed. So a remark about this definition, you have to be a little bit careful because, so the remark is that sets are not doors. Sets don't have to be either open or closed. They can either be both or neither. So to illustrate, well, this subset of R is neither open or closed. And on the other hand, any topological space contains, well, for any topological space, the whole space and the empty set are both open and closed. So they're open by what it means to be a topological space, and then they're closed, well, either trivially in the case of X or vacuously in the case of the empty set. Okay, so this is maybe a bad bad choice of terminology for open and closed, since you don't have this seemingly obvious thing that things are either open or closed. But nevertheless, there is a relationship between open and closed sets, which I'll state as the following proposition. So for a subset of X, A is closed if and only if the complement of A is open. Okay, so let's prove this. Okay, so, all right, let's start with the forward direction. So we're assuming A is closed, and let's fix a point in A complement. What we'll do is we want to show that there exists an open set with X contained in U contained in A complement. Okay, so how do we do this? So this follows quickly from the subset trichotomy. So by the subset trichotomy, X and A complement, well, it can either be a exterior point or a limit point, because the other two options, interior point and isolated point, those points are always in A. And A is closed implies X is not a limit point. And so X is an exterior point, which means exactly that there's an open set around X, which is contained entirely in A complement. Okay, and then let's do the converse. So A complement is open So, okay, this is similar. I mean, this means that every point is an exterior point. Every point of A complement is an exterior point of A. And so then the limit points of A are all in A. Okay, so as a sample application of this proposition, I'll leave you with the following exercise. So a map F from X to Y is continuous if and only if F inverse of A is closed for A in Y closed. So remember, we define continuity as the pre-image of an open set is open, but using this proposition, you can show that this is equivalent to the pre-image of a closed set being closed. Okay. All right, so now I want to switch gears and talk about something slightly different, which is the notion of a basis for a topology. So this is an analogy to the way that one understands a vector space. By choosing a basis, you can understand a topology on a space in terms of a basis. So let me give you the definition. So X, a topological space with, so let's denote U in the power set of X, the open sets, collection of open sets. Then we say that B, a subset of U, is a basis if every open set is a union of open sets in B. So that is to say, if U is in U, there exists some collection, let's say B alpha in script B, so that U is a union of these B alphas. Okay, so being a basis means you can write all open sets as unions of elements in the basis. And you can see this is somewhat an analogous definition as being a basis for a vector space, although there's no uniqueness here. So for example, if we have X is R squared with the standard topology, then the open balls of radius, so this is a basis. So this forms a basis. So here R is greater than 0 and X is any point in R2. This is essentially by definition. This is how we defined open sets. Open sets are sets so that you can find around any point in that set a small ball around it. And hence that open set is a union of all of these small balls around each of its points. But there's other choices of basis. So open rectangles, so sets of the form some interval times some other interval, these also form a basis. And the reason is, well, because any open ball around a point X contains a smaller open rectangle, or square even, around X. Okay, so if you're a union of open balls, then you can also be written as a union of open rectangles. Let me tell you one more basis. Let me move this here. Another basis is the set of balls around X, where now we insist that X has rational coordinates and R is rational. R is rational, still greater than 0. This is also a basis. Yeah, essentially because, any rational, on the real line, any open set around a rational point or irrational point contains rational points. So the nice thing about this basis is that it's countable. It has countably many elements. Okay, and now let me tell you, let me give you an example of why bases are convenient to work with for proving things about a topological space. In particular, here we'll be talking about continuity. Okay, so let's take X and Y spaces. And let's assume we have a basis B for the topology on Y. And okay, so that's the setup. So then F from X to Y, this is continuous if and only if the preimage of any basis element is open. The preimage of any basis element is open. So F inverse of B is open for B in this basis. So we don't need to check on every open set. It's enough to just check on the basis elements. So proof. Well, this direction is immediate because, well, if F is continuous, then the preimage of any open set is open. And in particular, the basis elements are open sets. Okay, so the more interesting direction is the reverse direction. So let's let U and Y be open. We want to show its preimage is also open. And well, since we have this basis, we can write U as a union of elements in the basis. And then, well, the preimage of U, so now we write this as the preimage of this union. And, well, the preimage of a union is the union of the preimages. So let's think about that. This set here is saying all the points that map into at least one of the B alphas. And well, you can break that up into things that map to each individual B alpha. So that's this things that map into some B alpha. Okay, and then, well, this is a union of open sets. These sets are open by assumption that, by the assumption on the right-hand side here. And so the union is also open. And that's it. Okay, so let's use this in an example. So let me create a new page. Erase the proof. So an application. I'll call it an application. So let's consider the exponential map. So this is a map from R to the circle, which we'll view as the unit circle in R2, which sends t to cosine t sine t. Okay, this is called the exponential map because if we view R as C, then we can write this as e to the it. But okay, so let's prove that this map is continuous. Well, so one way you could argue this, if you put on your calculus or analysis hat, is that, well, cosine and sine are continuous functions. And so this function has continuous coordinates and it's a continuous function. But, well, we should be wearing topology hats in this course. So let's give a topological argument that doesn't rely on needing to know anything about cosine and sine. So let's start by describing a basis. So okay, so this is proof. So there's a basis for the topology on S1 given as follows. So remember the topology on S1, we're giving it the subspace topology of R2, and well, open sets are, well, you get open sets by taking an open set in R2 and intersecting it with the circle. And so in this way, you can get little intervals on the circle, and these form a basis for the topology. Essentially because the open balls in R2 form a basis for that topology, and that's what you get when you intersect to the circle. So for θ1 less than θ2 in R, real numbers, let's say with θ2 minus θ1 less than 2 pi, consider B θ1 θ2 as the following subset of the circle. Well, it's all of those points with angle between θ1 and θ2. So, okay, so you have the θ1 line, and then maybe there's some other θ2 like this. And well, all of the points with angle between theta 1 and theta 2, that's what we'll call B theta 1, theta 2. Okay, and as I was saying a second ago, these form a basis for the topology on S1. So in order to prove this map is continuous, all we have to do is to show that, show that the inverse image of B theta 1, theta 2 is open for each theta 1 and theta 2. Okay, so let me do this on one last page. Well, right. So F inverse of B theta 1, theta 2. Well, yeah, so let me first draw a picture. How does this look? So here's, let me do 2 pi, 4 pi, and so on. So this map is periodic in the sense that if you have points that differ by 2 pi, then they map to the same point on the circle. And so, well, right, the inverse of this B theta 1, theta 2 is a union of intervals. It's, so let's say in this picture, well, okay, so let's say here's theta 1 and here's theta 2. So certainly this interval maps to B theta 1, theta 2, but then there's also the translate of this. This is like theta 1 plus 2 pi and theta 2 plus 2 pi. And okay, also adding 4 pi or minus 2 pi, minus 4 pi, etc. So in a formula, this is a union of, so theta 1 plus 2 pi k to theta 2 plus 2 pi k over k in the integers. And these are open sets in R. So this is, so F inverse of, or let me just say it this way. So this is union of open intervals, hence open. Okay, so okay, so this is how you can prove this exponential map is continuous just in the language of topology. Okay, so next time, that's all for today. And next time, we'll be talking about more about bases, and then we're going to begin talking about compactness.